Hello, you beautiful people. Today I want to talk to you about how you can do the reactor sizing for the ammonia process. And this time we will do it just by like manual. And in the next lecture, I will show you how to implement it in DWSim. But first, I want to show you the old-fashioned way. Okay, what do we need? We need something like a mole balance for the plug flow reactor, and then I can show you the reactor sizing using the conversion temperature diagram. And afterwards, I think you already guessed it, a little bit of homework so that you know how to spend your weekend. Okay, so maybe you ask yourself, why did we start with this weird conversion temperature diagram? So why not plot the mole fraction or whatsoever? Why is it conversion? And so normally you would say I'm more interested in the mole fractions. So then I know, okay, I have like 20% of ammonia at my reactor outlet. So why not go this way? And the reason for this is if you have a look at the mole balance of your plug flow reactor. So if you say, okay, I have a look at my plug flow reactor. Here I have the inlet mole flow. I just stressed out the initial mole flow of nitrogen at the inlet. Since this is our base component, so you have here also entering hydrogen inerts whatsoever. Then you have your plug flow reactor with the value with the volume V. And at the outlet, you may want to know your conversion of nitrogen at the outlet. So if you cut out a slice of this plug flow reactor, so this is a very small slice, so let's call it dV. Oops, let's call it dV. And if you then do a mole balance, then you have the inflow of nitrogen to this volume element. Then inside this volume element, you have the reaction rate. And the reaction rate, or the amount of nitrogen that is consumed here, this is the reaction rate times the volume slice. And then you have an outgoing mole flow of nitrogen. And let's say, okay, there should be a small change in this mole flow. That's why we say, okay, mole flow plus this very small change. Then you can do a balance. You say, okay, the mole flow leaving the reactor should be the nitrogen going to the slice of our reactor minus minus the amount of nitrogen that is consumed by the reaction. So we know already in advance that nitrogen is consumed. That's why we have a minus R here. So this means that it should be consumed. And then, okay, you find out that our mole flow nitrogen cancels out, and then you have just, okay, our very small change in the mole flow of nitrogen. This is equal to the reaction rate times the size of the slice here of our volume dV. Okay, and then you can rewrite it in terms of our conversion. If you don't see it at a glance, maybe just a few lines about it. So you can say, okay, our conversion of nitrogen, this can be written as 1 minus n dot n2 divided by n dot n2 at the inlet. Oops. Okay. And then if we want to have a small change, if we want to have d, so a very small change of our conversion of nitrogen, so then if you have a constant and you want to know the change, this will stay constant, so this cancels out, and then you have minus d n dot n2 over n dot n2 0. So this is a constant value, this is the mole flow at the inlet, so this isn't changing. And then you can say, okay, if I want to know my minus d n dot n2, this is the same as n dot n2 0 times, whoops, dx n2. So, and this is what we put in here. Okay, so now we have a differential equation, and so we can just write here the integral sign, and then you know, okay, your total reactor volume you get by integration. And since this is a constant value, you just have to solve the integral of 1 over r. So 1 over r you put on the other side, 1 over r dx. Oops. And your integration limits are 0. So you start normally with 0 conversion at the inlet, and you have your, then you have your outlet conversion, which is x and 2 out. Okay. And that's the reason why we decided to go for a temperature conversion diagram. So since in this diagram we have the relationship between our reaction rate and our conversion, and yeah, we can use this to calculate our volume. So it's not that straightforward, but at least we are quite close. Okay, mole balance. So and we need to solve this integral. So if I plot right now a diagram that looks like this, if I have my conversion on the x-axis, and here I have my 1 over r, we will see that for ammonia synthesis, this might look like this. Here you have the equilibrium, so it's not possible to go to 100% conversion, but there will be something like the equilibrium conversion. You already know this, and yeah, if I want to have this expression here, so this means we need the area under this curve. So 1 over r on the x-axis, and then you integrate it by your conversion. So this area here is our integral. And yeah, so you get something like this, but what I always do is just trying to find out, okay, what might be the value of the rectangle having the same area than this red area. So, oops. So maybe something like, this. So this would be the area here. This would be our x and 2, for example, equilibrium, or our outlet conversion times 1 over r average times 1 average. And I'm just trying by judgment to say, okay, what does it mean? So the area here and the area here must be the same as these two areas. And hopefully this fits a little bit. Okay, this was how it should look like. Now let's have a close look how we can do it with our conversion temperature diagram. Okay, here we see for our example 200 degrees Celsius as the inlet temperature. We can see how our temperature would evolve. Here we have our equilibrium. Now let's take this one. So here we have our equilibrium. So X equilibrium. This might be something like 0.47. And then you just go here and try to figure out these values. So for example, you can go here and say, okay, I have the reaction rate. The reaction rate is 10 to the power of 0.5, and I have a conversion of 0.9. I can go here. Here I can see, okay, this is something like 0.16, and the reaction rate here is 1, so 10 to the power of 0. And yes, I can also go here. Here I can see my x is 0.44. And yeah, how to guess the reaction rate here. So we are somewhere in the middle between 10 to the power of 0.5 and 10 to the power of 1. So this might be here a reaction rate of 10 to the power of 0.75. Okay, and you can do this for other points, and then you might end up with a table that looks like this. So I did the same as I showed you in the video. I just took the graph, and then I try to get the reaction rates in kilomole per cubic meter hour. So you just write it here. Here's our equilibrium. Our equilibrium conversion, and here I just took a big value that fits kind of good to the diagram on the next slide. So, and then for this diagram here, we need not the reaction rate, but we need the inverted reaction rate, so 1 over R. And this is the third column that we have here. So, whoops. So if we say, okay, our reaction rate is, where is it? Maybe here, it's 10 to the power of 0.5. Then you can calculate it, invert it, and then you get a inverted reaction rate of 0.316. And this you can put in a diagram, and then you have your 1 over R. You have it on the y-axis, and you have your conversion on the x-axis. So then you get a curve that looks like this. And what I did is I just somehow estimated that maybe this curve here, and so it's very, very small, this curve here should be equal to this area here. If I do this, then I have my rectangle, and then I can very easily calculate this integral here. So, and for our case, this would mean, okay, our reaction volume is our mole flow. So this should be 21 mole per second times our integral. And we say, okay, this integral is the same as our rectangle. So we say our average reaction or average inverted reaction rate is 0.85. The units are cubic meter hour per kilomole times our conversion in equilibrium. This is 0.47. Okay, what you have to take care of are the units. If you look here, you have in front, you have mole per second. This is the mole flow. And here you have kilomole and hour. So if you want to convert it, then you have to take into account the factor of 3.6 to take care of mole, kilomole, hour, and second. And if you do so, then you end up with a value that I didn't note down. It should be this one. Okay. Yes, so then you should end up with a value of 30.2 cubic meters. Okay, that's how you can get an like kind of estimation or reactor sizing for your reactor. Okay, and so that you can do the same, or that you can practice this. So it's nearly the same, but just a little bit of variation. So you shall repeat the calculation of the reactor volume, but this time for a temperature of 250 degrees Celsius, and we still have a pressure of 300 bars. Assume chemical equilibrium at the reactor outlet. This means you have to go to this diagram, draw the new line that might look like this until we reach equilibrium. So I remove it again, and then you have to create the table with the reaction rate and the inverted reaction rate, and then by the diagram you can judge the area of this new curve. Okay. And second part of your homework is determine the total inlet mole flow and the reactor volume for an ammonia production of 5 tons per hour. So this means you should stick to the same composition. So you still have 21% of nitrogen, 63% of hydrogen, 16% of inerts, and 300 bars. You have an inlet temperature of 250 degrees. But we want to have a reactor that produces 5 tons per hour of ammonia at the reactor outlet. And for this, I want to know the inlet mole flow, the total inlet mole flow, and the reactor volume. Okay, this is your homework. All the best and good luck for this homework. Thanks for watching.